This is the fourth section of chapter 6 of matrices, and this is how we can find the inverse of a 2 by 2 matrix. Now, what's special about an inverse is that if you multiply a matrix by its inverse, you get the identity matrix. Okay, so let's write that down. If we multiply a matrix by its inverse, we get the identity matrix. Remember, the identity matrix is that one that has ones along its leading diagonal. So we're actually talking about square matrices here. So we're going to be looking at 2 by 2, and then in the next section 3 by 3, finding the inverse. So it's basically a matrix. Let's call this matrix, they call it up here M. If we multiply it by its inverse, now the way that we denote an inverse is with that -1 here, so that tells us it's the inverse, like sine inverse, cos inverse. What's special about it, if we multiply them together, we get the identity matrix. That is, we get the matrix 1, 0, 0, 1 if we're finding the inverse of a 2 by 2 matrix, or we'd get this if we were finding the inverse of a 3 by 3 matrix. So a matrix times its inverse gives us the identity matrix. Okay, now how do we find the inverse? Well, it's up here, so let me just go through this. So if we've got a matrix, it's called a matrix A with the elements A, B, C and D, and I want to find its inverse, then the inverse A with a -1, what we do 1 over the determinant. Now remember how we find the determinant of a matrix? That is AD minus BC, so that was in the previous section, and we multiply that by, now we need to do something to the elements in the original matrix. Now what we do is these two swap over, so we swap over the elements A and D, so it's D and A there, and then what we do is we reverse the signs of these two elements, C and B. So we'll get -C and sorry, not -C there, that's -B, we're just reversing its sign, keep the position the same, and -C. And all of this will be the inverse, 1 over the determinant times by the matrix with elements A and D swapped over, and with the signs reversed for elements B and C, whatever those numbers are. What we'll find is that if we were to multiply that inverse matrix that we get from here with the original matrix, then we will get 1, 0, 0, 1. Now remember, we talked about the determinant, what happens when it's 0 or non-zero. Now you can see that here, if the determinant is 0, we can't do 1 divided by 0, it's not defined. So if the determinant of the matrix equals 0, it has no inverse because we can't do 1 divided by 0, so no inverse. So that's when we call the matrix singular. We did that before. You may not have wondered why we called it singular, but it's singular because we do 1 over over 0, which we can't do. There's no inverse, so it's singular. It doesn't have like its sort of partner to go with it, so it's like single. Right, so each of the matrices A, B and C determine whether or not the matrix is singular. So all we need to determine is what's the value of the determinant. Is it 0 or not? So let's start with A. The determinant of A, well, that's AD minus BC. Okay, so that's going to be 3 minus -2. So I get a determinant of 5. Okay, so this is non-singular. Okay, and so we're going to find its inverse. So its inverse is going to be 1 over the determinant, 1 over 5, times by elements A and D swapped over, so 1 and 3, and the signs reversed in front of B and C. So the one becomes, negative 1 becomes 1. Now we can leave it like that. So this is the inverse of A. Or, since that 1 over 5 is what we call a scalar, we can multiply everything in the matrix by that fifth and write our answer as 1/5 minus 2/5 minus a fifth. Sorry, not minus a fifth. That will be actually a fifth, and then 3/5. Yeah. Now sometimes it's just neater to leave that scalar out the front, but you can write it in that form and multiply everything by a fifth. So that's the first one. So let's have a look at the second one. Determinant of B. So determinant of B, so that's going to be A times D minus B times C. Okay, that's 2 minus 2, which is 0. So this is singular, so there is no inverse, because we would end up doing 1 over the determinant, 1 over 0, and actually, we can't do that. We have to leave it there. And then the last one is determinant of C. Let's see if this is non-singular or not. So this will be A times D minus B times C. So we end up with basically 0 minus 6. So you end up with a determinant of negative 6. That's fine. You can have a negative. So that means it's non-singular, which means we can find an inverse. So we apply what we call like the algorithm, the steps to finding the inverse. So C inverse is going to be 1 over determinant, so 1 over minus 6, so we can write it as negative of 6. Then inside the matrix, we take C and we swap over A and D, and we reverse the signs of B and C. So again, we can leave our answer like that. Sometimes it's preferable to leave it like that. Or we can actually work out negative of 6 of each element, so that stays as 0. Then you've got the negative 3 times by 6. That will basically be a half, because you'll end up with like 3 over 6. Then we'll end up with like 2 over 6, which is a third, so I'm simplifying it, and then negative 1/6. So there we go, we found the inverses. Now let's just pick one and see what happens. Let's just take this A, 3, 2, negative 1, 1. Let's multiply it by its inverse and see what happens. We should get 1, 0, 0, 1. That's the definition of an inverse, isn't it? Right, let's multiply them. So we will do 3 times a fifth, which is 3/5. So we're going to do this times that. That's 3/5. Plus 2 times a fifth, which is 2/5. So 3/5 plus 2/5 is basically 5/5, which is 1. So we get 1 there. Okay, let's go to the next one, next second column, first row. 3 times negative 2/5 is negative 6/5, and then 2 times that is plus 6/5. So negative 6/5 plus 6/5 is 0. It's looking good so far. Let's carry on. Moving down to the second row, first column, negative a fifth plus a fifth is 0. Write that in a minute. And then this is going to be plus 2/5 minus 3/5. Plus 2/5 plus 3/5 is going to be 1. So it works. Yeah, that's definitely the inverse. P and Q are non-singular matrices. Prove that PQ inverse equals Q inverse P inverse. In other words, the inverse of the product, what have we got here? And this is what we're trying to prove. So basically the inverse of the product equals the product of the inverses. The inverse of the product equals the product of the inverses. One of those sort of statements that basically means the same thing the other way around. Okay, so let's prove this. So let's start by calling the statement that's on the left, PQ inverse, let's call that A. Okay, and then what we're going to do, well, using the definition about a matrix times its inverse, next step would be, well, PQ times by the inverse of PQ, which is this here, okay, which we've just called A. So PQ, the product of that, times by A, that's going to be the identity matrix, yeah, because this is just PQ inverse. So basically we've times something by its inverse, the product of the matrices times by the inverse of the product, we get the identity matrix. Step one. Now we don't need the product, the brackets here. So PQA equals inverse. Now the order matters with multiplication. So the first thing I'm going to do is I'm going to multiply both sides by P inverse. Now if I multiply by P inverse in the front on the left hand side, I need to do the same on the right hand side, like this. So what happens is that this P and P inverse, they're going to cancel out. It just basically becomes the identity. Yeah, and if it becomes the identity, you can think of like them just cancelling out. And if that's the case, we're just going to be left with QA equals P inverse. Okay, so it's important to note here that where we have a matrix times by the identity, okay, we can cross out the identity. Yeah, you can think of it in a way like cancelling out, a bit like when you know, multiplication, you multiply and you end up timesing by 1. They sort of cancel out. So, you know, there was these two cancelled out here, and actually that became the identity here. So yeah, I could have written identity here and identity here, but think of it like cancelling out. I don't need to write them down anymore. Okay, or I could have said, right, P times its inverse is the identity. Then I've got the identity there, and then the next step would be to divide both sides by the identity matrix, and then that just leaves this. Okay, so maybe I've sort of missed out a step, but that's what you get. Now next thing we're going to do, we're going to multiply both sides by Q inverse, and I'm going to put that at the front just like I did before. So Q inverse at the front here in front of QA. I'm going to do the same with the other side, so the Q inverse must go in the front. You've got to do the same order on both sides. Now the same thing that happened before is going to happen again. Can you see those? Q and Q inverse. Right, what does that become? That becomes the identity matrix. So I suppose in the next step I could write identity times by A equals Q inverse P inverse. Okay, but it sort of cancels out basically, so I don't need to write that. I could write that out, and then in the next step just write A equals that. Now we're almost finished. What did we say A was at the very start, all the way up here? What did we say? We said our A was PQ inverse, or PQ all inversed. PQ all inverse, and what does it equal? Well, it equals Q inverse P inverse. Now this is an important result which is worth remembering, and this is only if the matrices are non-singular, because we're using inverses all over the place. So remember this: the inverse of the product is equal to the product of the inverses. But notice that on this side the order is not the same as this side, is it? Here we have A followed by B, but on this side we have B followed by A, so just be aware of that. So not sure whether you need to prove that in exam, but it's definitely worth knowing how to do it and to prove that result and remembering that result. A and B are non-singular, so they've got inverses, 2 by 2 matrices such as BAB equals the identity. Prove that A, B inverse, B inverse, prove that A equals B inverse times B inverse. So it's similar to what we were doing last time. So let's start with what we've been given. B, A, B equals the identity. Right, so the first thing I'm going to do is to do B inverse to the front of both sides. So I've got B inverse B, A, B. So on the other side, I'm going to have B inverse in front of identity. Right, now we've got this, that sort of cancels out. That becomes the identity matrix. Let's write it down this time. So identity A, B equals B inverse identity, like this. I suppose you could say, right, I'm going to divide both sides by the identity, and that will just leave AB B inverse. Now what I'm going to do now is I'm going to do B inverse to both sides, but I'm going to put it at the end because I want to get rid of this other B. So notice I put the B inverse at the end there. So on the other side I put the B inverse at the end. Now what happens over this side? Well, over here where we have B inverse B, that becomes the identity. It sort of cancels out. So all we're left with is the result what they wanted. A equals B inverse B inverse as required. Part B, given that B equals that matrix, find the matrix A given that BAB equals the identity. Now, we've just proved something, haven't we? We've proved that BAB equals the inverse, which tells us that A equals B inverse B inverse. So actually we're going to use the second statement to actually work out what A is. A is equal to B inverse times itself. So let's find B inverse. So B inverse is equal to 1 over the determinant of B times by elements A and D swapped and B and C signs reversed. Right, so let's work out what the determinant of B is. Maybe I should have done that first. That is AD minus BC, which is not equal to, minus BC. So that's 6 minus 5. So the determinant of B is 1. So that means that makes it nice and easy. If the determinant is 1, I've got 1 over 1. 3, negative 5, negative 1, 2. So that is just 3, negative 5, negative 1, 2. And A is equal to the inverse of b, which is 3, -5, -1, 2, times itself, 3, -5, -1, 2. Now, you don't square them, yeah, you actually multiply them together. So first element is going to be 3 times 3. So remember, we're going across and down. 3 times 3, 9. 9 plus 5, which is going to be 14. Next one is going to, if I go to the second column, so this is going to be 15 minus 10. Sorry, -15 minus 10. So that'd be -25. Going down to the next bit. Here, bottom row, first column, is -3 minus 2, which is -5. And then the last one down at the bottom here is going to be, this is going to give me 5 plus 4, which is going to give me 9. Okay, so this is a matrix A. So in this question, we were using the result from part A to help us do part B. And whenever you do these proofs, they're normally fairly straightforward. You just do the same thing to both sides, but make sure you keep the position of the matrices the same. So if I carry out something where, let's say I multiply by B inverse, for example, here in the front, you must make sure it's in the front here. If I do something that's at the end on this side, I must do it on the end on this side, because we said that the order matters. Right, you should now be able to do exercise 6D on pages 110 to 111 of the textbook.